Right now, beneath the freezing waters of the Baltic Sea, engineers are attempting something that has never been done before. They are lowering concrete blocks weighing 73,000 tons each onto one of the most unstable seabeds in Europe. Not one block, not 10, 89 of them, lined up end to end across 18 kilometers of open water, positioned with an accuracy measured in millimeters. One miscalculation, one unexpected shift in the ocean floor, one seal that fails under pressure, and $7.5 billion disappears into the Baltic. This is the Fehmarn Belt Fixed Link, the largest construction site in Europe, a tunnel that will reshape how goods and people move across an entire continent. But what most people do not know is that this project was blocked for over 20 years. Lawsuits, political warfare, an entire industry spending millions to make sure this tunnel would never exist. Now, construction is racing toward a 2029 deadline. Massive factory-built elements are being floated out to sea and sunk into a trench, carved through layers of clay and limestone. Engineers are working against geology, against time, against critics who warn that the real problems have not even started yet. The question no one in power wants to answer is simple. What happens if this unprecedented gamble fails? If you are fascinated by massive engineering projects and the hidden risks behind them, make sure to subscribe to the channel and drop a comment below. Do you think this tunnel will actually open on time? Or is Europe betting billions on something that might never work? Let's get into it. To understand why engineers are taking such an enormous risk, you first have to understand what is at stake. Pull up a transportation map of Europe. Trace the path from the northern tip of Finland all the way down to the Mediterranean coast. That route stretches over 4,800 kilometers. It is called the Scandinavian-Mediterranean Corridor, and it is one of the most important economic arteries on the planet. Goods, freight, raw materials, manufactured products. Billions of euros in trade flow along this corridor every single year. But there is a problem, a bottleneck, a gap in the system that has been strangling this flow for decades. The Fehmarn Belt, 18 kilometers of open water separating Denmark from Germany. It does not sound like much, but for millions of tons of cargo and thousands of travelers every single day, crossing that strait is a nightmare. Option 1. Wait in line for a ferry. Load your vehicle. Sit for 45 minutes as the ship crawls across the water. Unload. Continue driving. Option 2. Skip the ferry entirely and take a 160-kilometer detour through winding roads to the west. Add hours to your journey. Burn more fuel. Waste more time. Both options are slow. Both options are expensive. And both options have been bleeding Europe's economy dry for generations. How much does this bottleneck actually cost? Some estimates put the figure at $80 billion per year. Not total. Per year. That is the cumulative price of delays, missed connections, inefficient logistics, and lost productivity. A figure large enough to fund dozens of megaprojects, all of it vanishing into wait times and detours at a single 18-kilometer strait. So why was this not solved decades ago? Why did engineers wait until now to attempt a crossing? The answer lies in what they discovered beneath the Baltic. The floor of the Fehmarn Belt is not ordinary seabed. It is a geological trap. Beneath the water sits a chaotic mixture of soft clay and hard limestone. Layers shift unpredictably. Pockets of different material appear without warning. The kind of ground that has destroyed tunnel boring machines on projects around the world. Engineers studied this seabed for years. They ran simulations. They drilled test cores, and the conclusion was grim. Sending a tunnel boring machine into these conditions would be a gamble with terrible odds. Soft clay sections would collapse around the cutting head. Hard limestone layers would grind the machinery to a halt. The risk of getting a billion-dollar machine stuck beneath the Baltic was unacceptably high. A bridge was considered, but the strait is a major international shipping lane. Any bridge would need to be high enough to allow massive cargo vessels to pass beneath. That meant enormous towers, enormous spans, and enormous exposure to the brutal wind, ice, and storms that sweep across the Baltic every winter. Neither option worked. For years, the project stalled. Engineers debated, politicians argued, and the bottleneck remained. Then someone proposed something radical. What if they did not drill through the seabed at all? What if, instead of boring a tunnel underground, they built the entire tunnel on land and then lowered it piece by piece onto the ocean floor? It was an audacious idea. The immersed tunnel method had been used before on smaller projects, but never at this scale. Never with elements this heavy. Never across a strait this long and this geologically unpredictable. The decision was made. They would attempt the impossible, but choosing this method triggered something engineers did not expect, a political war that would last 2 decades. You might assume that a project promising to save Europe $80 billion a year would have universal support. You would be wrong. Germany resisted this tunnel for over 20 years, and the reasons were not just technical. On one side stood Scandline, the ferry company that has operated the Fehmarn Belt crossing for generations. For them, this tunnel was not infrastructure. It was an extinction event. If cars and trains could cross beneath the water in minutes, why would anyone ever board a ferry again? Reports suggest Scanline spent millions lobbying politicians, funding opposition campaigns, and supporting legal challenges designed to delay or destroy the project entirely. Every permit, every environmental review, every approval process became a battlefield. Environmental groups joined the fight. The Baltic Sea is home to protected habitats, porpoises, seabirds, fragile ecosystems that construction would inevitably disturb. Lawsuits piled up in German courts, injunctions were filed. Construction was blocked again and again. Local communities on the German side pushed back too. Concerns about noise, disruption, changes to the coastline, the fear that a massive infrastructure project would permanently alter their way of life. And underneath all of this sat a fundamental imbalance. Denmark wanted this tunnel badly. Germany was far less enthusiastic. So Denmark made an extraordinary offer. They would fund almost the entire tunnel themselves. Germany would only be responsible for upgrading the roads and rail lines on its own side of the border. A treaty was signed in 2008. Politicians shook hands. The project was officially approved, but the lawsuits continued. The delays stretched on, and construction did not actually begin until 2020, more than a decade after the treaty was signed. Some analysts estimate that this political warfare added billions in inflation-adjusted costs to the final price tag. 2 decades of fighting over a tunnel that might have been finished years ago. Against all odds, the diggers finally broke ground, and what they are building defies belief. If you did not know about this political battle, hit like so more people can see what really happened behind this mega project. Before a single tunnel element could touch the water, engineers had to build something unprecedented on land, a factory. But not just any factory. In Rødbyhavn, Denmark, construction crews spent 2 full years building one of the largest production facilities the country has ever seen. A 500,000 square meter mega factory with a single purpose: to manufacture concrete elements so massive that nothing like them has ever been produced before. Picture the scale. The factory floor covers an area equivalent to 200 footballs fields. Inside, 89 tunnel elements will be constructed, each one measuring 217 meters long, 42 meters wide, roughly 9 meters tall, and weighing approximately 73,000 tons. If you stood one of these elements on its end, it would tower over most skyscrapers. Stack all 89 together, and the combined height would be twice that of Mount Everest. The production process is a marvel of industrial precision. First, workers assemble reinforced steel cages. Thousands of steel bars cut, bent, and tied together to form the skeleton that will give the concrete its strength. Without this internal framework, the elements would crack and crumble under their own weight. Once the steel cages are complete, they are lowered into enormous formwork systems, molds that hold everything in exact position while concrete is poured around them. Each 24-meter segment requires roughly 3,300 cubic meters of concrete. Workers spend 30 hours filling, leveling, and vibrating the mixture to eliminate air pockets and ensure uniform density. Then, the waiting begins. The concrete must cure for weeks, slowly hardening, slowly reaching the strength it needs to survive a century underwater. When the segment is ready, the formwork is stripped away. The segment is pushed forward along the factory floor, and the process repeats, segment after segment. 9 segments join together to form one complete tunnel element. The precision required is extraordinary. Any flaw introduced now, any crack, any weakness, any misalignment becomes a potential point of failure later. Deep beneath the Baltic, under millions of tons of water pressure, where repairs are nearly impossible, quality control teams inspect every surface, every joint, every centimeter of steel and concrete, because once these elements leave the factory, there is no second chance. But building these giants on land is the easy part. What comes next is where projects like this have failed before. Imagine carving a trench across the bottom of the Baltic Sea, 18 kilometers long, roughly 40 to 45 meters wide, 12 meters deep below the natural seabed. Now imagine doing it through ground that shifts between soft clay and hard limestone with almost no warning. Dredging crews have already completed this brutal phase. They removed nearly 20 million cubic meters of material from the ocean floor, enough to fill 8,000 Olympic swimming pools. The excavated sediment was pumped through pipelines stretching 2 kilometers to shore, where it was processed and stored. With the trench prepared, the next phase begins, and it is the most dangerous part of the entire project. Each completed tunnel element is designed to float. The ends are sealed with steel bulkheads, trapping air inside and giving the massive concrete block enough buoyancy to stay on the surface. Think of it as a 73,000-ton submarine made of concrete. Tugboats pull these floating giants out of the factory basin and across the open water to their installation positions. The journey is nerve-wracking. A structure that heavy, floating on the surface of the Baltic, is at the mercy of wind, waves, and current. Stability must be maintained every second of the transit. Once the element arrives at its designated location, immersion pontoons take over. These are floating platforms roughly 100 meters long and 45 meters wide, equipped with 66 winches and a lifting capacity of around 8,000 tons. Their job is to position the element with almost unbelievable accuracy. Millimeters. That is the margin of error on an element weighing 73,000 tons. When the element is aligned, the ballast tanks built into the structure are slowly flooded with seawater. The buoyancy decreases. The element begins to sink. Hydraulic sensors and GPS systems track every movement, feeding data to engineers who adjust the descent in real time. Too fast, and the element could land off target. Too uneven, and one end might settle before the other, creating stresses that could crack the concrete or misalign the joints. The sinking process is calculated in advance and executed with surgical precision. Once the element touches down in the trench, it must be joined to the previous section. This is where waterproofing becomes critical. Each element has thick rubber gaskets at both ends. When two elements are brought together and aligned, these gaskets press against each other, creating an initial seal, but it is not watertight yet. Between the two elements sits a small chamber sealed off by a temporary steel bulkhead. Engineers pump all the water out of this chamber, creating a pressure differential. Outside, the full weight of the Baltic presses against the new element. Inside the joint, there is no water pressure at all. The result is that seawater literally forces the two elements together, compressing the gaskets into a tight mechanical seal. Once the joint is secure, crews remove the bulkhead, install a secondary omega gasket from inside the tunnel, and pour reinforced concrete to lock everything permanently in place. The result is a watertight connection designed to last for over a century. But history shows that this process does not always go smoothly. Other immersed tunnel projects around the world have faced seal failures, flooding during installation, elements that landed off target and had to be repositioned at enormous cost. The Fehmarn Belt project is attempting this on a scale and weight class that has never been attempted before. Every element that sinks successfully is a small miracle of engineering. Every element still waiting in the factory is another opportunity for something to go wrong. Let me know in the comments. Do you think this installation method is genius engineering or a massive gamble? Even if every element lands perfectly, even if every seal holds, even if the tunnel opens on schedule in 2029, critics warn that the real problems have not even started yet. Start with maintenance. This tunnel is designed to last 120 years. That means for more than a century, engineers will need to inspect, repair, and maintain a structure buried 30 meters beneath the Baltic Sea. Corrosion, concrete degradation, seal wear, mechanical systems for ventilation, lighting, and drainage. All of it operating in one of the most inaccessible environments imaginable. How do you fix a problem at the bottom of the ocean? How do you even find a problem before it becomes a catastrophe? These questions do not have easy answers. Then there is the issue of safety. When it opens, the Fehmarn Belt Fixed Link will be the longest combined road and rail immersed tunnel in the world. Cars, trucks, and trains will pass through simultaneously. Thousands of people at any given moment, traveling 30 meters underwater through an 18-kilometer concrete tube. Now imagine a fire. Tunnel fires are among the most dangerous emergencies in transportation infrastructure. Smoke fills enclosed spaces within minutes. Heat builds to lethal levels. Evacuation routes are limited. Emergency responders face nearly impossible access challenges. The project includes extensive safety systems, ventilation designed to extract smoke, emergency exits, and cross passages, fireproof materials, and suppression systems. But critics point out that no amount of engineering can fully eliminate the risk of a catastrophic incident in a tunnel this long and this confined. And then there is the economy. Traffic projections assume that once the tunnel opens, behavior will change. Drivers will abandon the ferries, freight companies will reroute their logistics, the bottleneck will disappear, and the economic benefits will flow. But assumptions are not guarantees. What if ferry companies slash prices and compete aggressively? What if the tolls required to pay off construction costs drive travelers toward alternative routes? What if the projected demand simply never materializes? The tunnel is being financed primarily by Denmark, with the expectation that toll revenues will eventually repay the investment. If traffic falls short of projections, Danish taxpayers could be left covering the gap for decades. Climate adds another layer of uncertainty. The tunnel is being built for conditions that exist today. But what about conditions a century from now? Sea levels in the Baltic are projected to rise. Storm intensity is increasing. The long-term environmental pressures on this structure are impossible to fully predict. Finally, there is the environmental toll that has already been paid. Construction has disturbed protected marine habitats. Dredging has reshaped the seabed. The long-term impact on porpoise populations, fish breeding grounds, and coastal ecosystems is still being debated by scientists. Supporters argue the benefits outweigh the costs. Critics warn that the true price will not be known for decades. So, with all these unknowns, where does the project actually stand right now? Subscribe if you want updates on whether this project actually opens on time, or if the problems are just beginning. As of now, the Fehmarn Belt Fixed Link is further along than skeptics ever expected. The seabed trench is complete, 18 kilometers of ocean floor carved out and prepared. The mega factory in Fehmarn is operating at full capacity, producing tunnel elements on an assembly line schedule. The first elements have already been floated out to sea, sunk into position and joined together beneath the Baltic. The target date remains mid-2029, a full opening for both road and rail traffic, but 79 standard elements and 10 special elements still need to be manufactured, transported, sunk, and connected. Each installation is a high-stakes operation. Each joint must be sealed perfectly. Each section must align with millimeter precision, and mega projects of this scale rarely finish on schedule. Cost overruns are common. Delays are almost expected. The political and legal battles that held this project back for 2 decades could flare up again if anything goes seriously wrong. If the tunnel opens successfully, the transformation will be immediate. Travel time between Hamburg and Copenhagen will drop from 4.5 hours to under 2. Freight that once crawled across ferries or detoured through winding roads will flow directly beneath the Baltic in minutes. The bottleneck that has strangled European logistics for generations will finally be gone. Scandinavia will be fully integrated into the continental European transportation network for the first time in history. Trade will accelerate. Tourism will surge. The economic benefits could ripple outward for decades. But if the project fails, if a critical element lands off target, if a seal fails and flooding forces a shutdown, if costs spiral so far out of control that the tunnel becomes a financial black hole, the fallout would be enormous. Billions of euros lost. Political careers destroyed. A symbol of European ambition transformed into a cautionary tale about overreach and hubris. The next 5 years will decide which story gets told. By the end of this decade, the Fehmarn Belt Tunnel will either stand as the greatest engineering achievement in modern European history, or it will serve as a warning about the limits of human ambition. Right now, beneath the freezing waters of the Baltic, engineers are racing against forces they cannot fully control. Geology that shifts without warning. Political currents that could turn hostile again. Economic pressures that may not unfold as planned. A climate that is changing faster than anyone predicted. Every element that sinks successfully brings the project closer to triumph. Every delay, every setback, every unexpected challenge brings it closer to failure. The decisions made in the next few years will shape European infrastructure for a century. And one question still hangs over everything. Can human engineering outpace the chaos of nature, politics, and time? If you want more, deep dives into the mega projects shaping our future, the hidden risks, the engineering battles, the stories no one else is telling. Subscribe to the channel and hit the notification bell so you never miss an upload. Like this video if you learned something new. And tell me in the comments, do you believe this tunnel will open in 2029, or will Europe be waiting even longer? Thanks for watching. I will see you in the next one.